Hi, John. We can see everything.
Hi, Tatiana, how are you?
Okay, struggling to run seminars in online situation when you don't see what students do.
Difficult. It really is. Right, it's my last lecture of new material today, so I'm a week behind you. Have you got my
Yes, I
email
did.
and contents?
Yes, I did get your email, and I'll sort out and submit.
What
Thank
do you
you, John.
think what do you think of the approach?
I drew very similar approach than you.
I don't know how it's going to go down.
Uh, let's see, because it's the only way how what we can do.
Yeah, yeah,
And what we need to do, we need to do a lot of practice exercises for the students, like
yeah,
doing practical things like I'm doing at the moment.
yeah, yeah. We can only do our best. We'll talk offline about this because students might
Yeah,
be
yeah, yeah,
listening.
definitely, definitely, definitely.
Okay, guys, it's 10:05. And it's time to start. Let me get set up properly. Hi. I trust you're seeing and hearing me. Right, folks, this is the last week when I will be giving you new material. And so after this week, we'll be in revision seminar mode. The way I handle revision seminars is I want you to make suggestions of topics, the same as we did in level 1 at the end of the course. And I will go over the things that you are not clear with or want further explanation on. I want you to drive the research seminars because if I'm giving you material, two situations could occur. One could be I will be concentrating on the material in the exams, and that would be possibly not right. The other thing is I might be spending a lot of time on something that is not in the exams. So to try and remove that bias, you drive it and I'll explain. Okay, the last topic I want to talk about, it's a huge topic and I just want to give you an introduction to it. It's important, you're using it every day, and it is content-based retrieval. Let's get the pen a bit thinner. CBR, which is content-based retrieval. Okay, there's the CBR coming out of it. Now, what's this all about? It is where you have a picture and you ask the question, find me pictures similar to this. It's on Google, it's happening all the time, searching by image content. And we do it all the time as humans. We don't have date stamps on our pictures. If you look out the window and see a tree or a house or a person, there's no date stamp or title to search it on. You recognize that from your memory bank. So how do we do it? Right. Most of the work was done by IBM. Oh, don't go. Oh, you blasted thing. Oh, I'm fed up with this whiteboard. I'm afraid you're getting used to my swearing now, aren't you?
Oh, come on, everything is fine.
Bloody thing. I'll
Yes,
find
you
out.
can see Dimitros.
Yeah.
There is a screen sharing, so please double check and refresh your screen if you cannot see.
No, I've got it back. If somebody can give me a way in Microsoft Whiteboard to fix the zoom and freeze it so I can just scroll up and scroll down, I'll give you 20 quid. There you are. There's a promise to you. It's got to work.
Oh,
Okay. IBM are the people who did most of the research in the early days on content-based retrieval. And their system was called Cubic. So you can actually do a search on Google for Cubic. And Cubic is query by image content. There's your Cubic coming out. And they had 4 approaches to content-based retrieval. And their 4 methods were: one was by color. The second was by shape. The third approach they used was texture. And the fourth was by sketch. And they were exceedingly less successful. The most successful was color, and the most difficult was retrieval by sketch. So let's first of all look at color retrieval. And the approach is obtain the color histogram. Of image. This is the image you want to search. You've got this image, you want to find similar patterns or similar pictures like this image, you obtain the color histogram. And we are going to apply this to real images, not silly 3x3 examples. And a typical real image would be 4,000 by 4,000 pixels, and it would be full color. And how many colors are there? Well, most people, or some people, I'm sure none of you will come back to this or give this answer. Some people will say there's 3 colors, red, green, and blue. But no, those are the color types. And we are looking at the individual shades of color. And the number of colors there are on the standard image is the pixel is 24 bits, and it is 8 bits red, followed by 8 bits green, followed by 8 bits blue, which gives us a 24-bit number. For each pixel. Right, now a 24-bit number is going to give a huge number of colors. It's going to be 2 to the 24. And if you work that out, it is approximately 16 million, which is quite a lot. So we've got a image resolution of 4,000 by 4,000. That is also going to be of the region of 16 times 10 to the 6 pixels. So we're hitting the problem of big data again. And to get a full color histogram, it is almost impossible. Oh, smaller. Because it would be a histogram which would have the numbers could go up to 16 million if it was just a single color, and the number of there's a number of occurrences, and the horizontal axis will be the color, and the color would range from 0 to 16 times 10 to the 6, and that would result in a huge histogram, difficult to handle, very sparse because we're distributing 16 million pixels over 16 million states, and you'd be lucky to have more than a few at the precise same color. So this is impractical, impossible. So how can we approach this in a more sensible way? So the solution. Reduce the color resolution. And so if we're taking a pixel value, say Pij, it is going to be 24 bits. Let's draw 24 bits out. Supposing it is 1, 0, 0, 1, 1, 1, 1, 1. That is going to be the red. Haven't got a green pen on my list, have I? Can't find a green pen. Okay, carry on with the red. Let's have another 8 bits. 0, 0, 1, 0, 1, 1, 0, 1, 0, 2, 4, 6, 8. That can be the green content. And the blue content, 1, 1, 0, 0, 1, 0, 0, 1, 1. There is the blue. That would be your 24 bits. Reduce it to a lower resolution, say 3 bits per color plane. We would take the most significant 3 bits of the red, extract the most significant 3 bits of the green, and that should disappear. And there's the green, and there's the blue. Take those together, give a reduced color resolution of 1, 0, 0, 0, 1, 0, and 1, 1, 0. That would be 9 bits. And 9 bits is going to have 2 to the 9 states, which is 512. Your histogram would be a much more reasonable histogram with the number of occurrences there, and the colors would go from 0 to 512, which is the range on 9 bits. Okay. Right. Having got the histogram, convert the histogram to a vector. And that would give you a pattern vector x, which would go from x0, which would be the number of pixels at
Please be with me. I will try to sort out what is the problem.
an alternative approach to the reduced color resolution, because you will be losing some color information.
John,
Hello?
John, you disappeared for a bit, so we missed a bit of what you said.
Ah, okay.
John, you've been disconnected. I was just trying to dial you in.
Ah, sorry, folks. I've been disconnected. Can you hear me?
Yeah, we can hear you now, but you disconnected like after the 9 bits part.
Can you? Okay, let's go back. Right. We're reducing the color resolution from 24 bits to 9 bits. Okay. That will give us 2 to the 9 states, and those states are actually 0 to 511 on 9 bits. Having got the reduced resolution, you can plot out a color histogram on the reduced resolution. So the color histogram would look as normal, something like that. Values for each color, and the number here would be the number of occurrences of that color. Having got that histogram, we go to a vector. And the vector simply is the amplitude or the horizontal value of each color value from 0 to 512 to 511, a 512 element vector. Once you've got a vector, you know how to classify vectors. Use the distance classifier to find the closest match. This is your pattern that you are interested in. You want to find patterns in a database similar to that pattern. The database has to be converted to histograms. Then you can do a distance search between the pattern you're looking for and find the nearest pattern in the database, which is closest to your pattern. And that should give you a similar pattern to what you're looking for. And then I just said, still there? I then said a little bit of revision, distance classifier, the Euclidean distance is the true distance. And just to remind you, the equation of distance, Euclidean distance between A and B is the square root of the summation over all dimensions of the sum of the difference between corresponding elements squared. And that is really multidimensional Pythagoras theorem. Okay, so that's one method. The second method. Use a composite histogram. Clearly, with the color reduction resolution, we are losing information. So this is an alternative, which has some advantages and some disadvantages. Right, the composite histogram. We take the red plane. It will be the first 8 bits of your 24-bit per pixel coding. It will range from 0 to 255. And you simply take the red plane and get the histogram of the red distribution, which might look something like that. And that will occupy 256 elements. Having got the red distribution, we then get the green distribution. Let's have that going from 0 to 255. And this would be the green. Somebody's phoned up. And again, we get a distribution like that. Now, in terms of the running calculation, this would be 256 to 512, I think. Yeah. Then add the blue. And the blue is going to be 0 to 255. And there is going to be the blue histogram. And on the running counter, on the axis, this is going to be 513. I think that goes up to 567, 68. So we've got 768 elements in that vector, in that histogram. Now that's manageable. It's much better than going for the full color, which would have been 16 million color types. So, having got that, again, the same process, histogram to vector. In this case, we're going to get a pattern which is going to go from x equals x0, which will be the value there, right the way through to x 768, which will be the vector point there. And a few hundred elements is manageable. Right. We're not losing any color resolution, but there is a hidden problem with this approach, and this is color matching. And I'll give a very simple example to try and show you what the problem is. Let's take 2 patterns. I'll go black. There is a pattern, and it's going to be a very idealized pattern. I want half the pattern, to be absolute red, maximum red. And the other part of the pattern to be, why haven't I got a green pen on this whiteboard? I have to be grey. And the other part of the image, maximum green. So that is pattern 1. Oh, come on. And for pattern 2, I want to give you a completely different visual pattern. I want the same area and the top half of the image to be yellow, maximum yellow, bright yellow. And the bottom to be black. Right, now to a human perspective, those are totally different patterns. Let's apply the composite histogram to this. First for pattern 1. For pattern 1. Let's have the histogram, and I would subdivide it into 0 to 255 for red, and 0 to 255 for green, and 0 to 255 for blue. And of course, the running count will go up to 768, I think it is. Right, for pattern 1. The pixel, and let's express the occurrence as a percentage. So let's have 50% and 100% of the pixels, which is convenient for this image. Right, looking at image 1, the red value of all the pixels in pixel 1. Well, half the image is absolute red. So we will have 50% entry in absolute red. The other half of the pixels in the green area of the image, the red plane will be 0. There is no red content in absolute green. So we will have 50% of the pixels of the red plane at 0. Now let's have a look at the green content. Right, there's going to be 50% of the pixels maximum green. Which are in the green half of the image. Now the green content in the maximum red is going to be 0, and that's going to be half the pixels. We will have an entry of 50% on 0 green. Now let's have a look at the blue content in image 1. There's no blue in the red, there's no blue in the green. So for the whole of the image, 100%, the blue plane will be 0. So the entry for the blue plane is that. So that is the histogram. It's sparse. It only has 1, 2, 3, 4, 5 values in 768. Of course, a real problem, there would be a spread of patterns because one wouldn't have such idealized images in nature. Right. Let's now have a look, see if I can shrink this without it going mad. Let's have a look now at pattern 2 and get its composite histogram. Reduce it a little bit. Right, yes, I think I can just do that there. Now for pattern, this is for pattern 1. Now for pattern 2, same histogram. 50%, 100%. And the pattern ray, let's just let it reduce a little bit more. Behave yourself. Right, and the same horizontal axis, 0 to 255 red, 0 to 255 green, and 0 to 255 blue. Okay, looking at the yellow and black, you need to know from your color theory, I'm sure most of you do, yellow is not a primary color. Yellow is made up of red plus green. Assuming it is emitted light. If it's absorbed light, it's different. Okay, we're now looking at the red content in pattern 2. In the yellow area, we will have maximum red. So 50% of the pixels will be maximum red. And in the black region, 50%, wrong one. 50% will be maximum red, and in the black region, the other 50% will be 0. So we've got 2 entries there. Now for the green, in the yellow region, the green is maximum green, 50%, and the other half will be the green in the black is going to be 0, and that will be 50%. Now for the blue, there's no blue in the yellow pixels, there's no blue in the black pixels. All the blue content for 100% of the pixels is 0. So there will be 100% on blue. So if I draw those to scale, 1 and 2 are exactly the same. And that accounts for some interesting things. If you're doing image searches, if you're doing it on Google, search on the image, you get some pretty good matches, but occasionally there'll be a picture which is totally different. And it's got no perceptual similarity to the pattern you're searching for. And there's an example, an extreme example of what would happen. The yellow and the black image will be classed as a red and a green image because of that color mixing. So that's a disadvantage of the composite histogram, but it's easy to process and it does work. So that is the searching by color, and it's still research to be done to improve it, but it's an interesting topic. Now the second approach, how are we doing for time? Halfway through, that's good. No, it's good, I've got enough time. The second approach is retrieval by shape. And this is tended to be used for artificial images. Rather than natural, such like industrial shapes. And I won't spend too much time on this because it's a little bit specialist. Again, it's histogram based, and this will be the number. And we want a horizontal axis which is measuring an aspect of shape. And the horizontal axis we will use is the shape factor. Again, that shouldn't be a new term to you because that was in one of the earlier lectures. The shape factor for shapes, S is going to be equal to P squared over A, where P is the perimeter and A is the area. And if we take the smallest shape factor, is going to be a circle, and for the circle, S is going to be the perimeter, which is 2 pi r, all squared divided by the area, which is, well, I'll put that down, the area which is pi r squared. Sorting that out, 4 pi squared r squared over pi r squared. The size dependent factor goes, a pi goes, and we are left with 4 pi, which is approximately 13. Now for the shape factor here, if I'm using this raw shape factor, it will start at 13. There will never be a value below 13. Well, we could live with that, but for convenience, we can have a normalized shape factor. And that is defined as S equals P squared divided by 4 pi and the area. Exactly the same properties, except the minimum value for a shape factor now becomes 1 instead of 13. So that was the parameter that go on the shape factor. And having done that, we get our shape factor from 1 to whatever it is, x. Normal histogram. So the same process, histogram to vector and distance classifier. So that gives us a way of picking up the number of images that have lots of circles in them, or lots of squares, or lots of metal parts that might have a fixed shape. Third method, retrieval by texture. And retrieval by texture, again, it's an extension of texture recognition, which we've done recently. We have an image, we have an operator. Let's take a 4-pixel operator operating around a central pixel with A, B, C, and D, the pixels around it. So there is the operator in your image. And it scans the image up and it scans the image down. Ranking them, because we know texture is a difficult thing to represent with 1 bit per pixel. So scan. This is a bit of revision of texture recognition. We then rank. And remind you, the ranking operator takes the values of A, B, C, D, and according to their order, A is greater than or equal to B, is greater than or equal to C, is greater than or equal to D, becomes a rank. Let's call it rank 1, which might have a number. Let's just write it down in binary as 1, right the way through to the opposite, which is D, is greater than or equal to C, is greater than or equal to B, is greater than or equal to A, and that would be rank, I think, 24, and that would be 16, 8, 0, 0. And so we've got a binary value, which can be the state, and that would be the horizontal axis of the histogram. Why is there 24? Because the number of ranks we have a choice of 4 being the brightest, the highest intensity, times 3 being the second highest, times 2 being the third highest, and the darkest one, it's only one choice. And that, of course, is 4 factorial for a 4-pixel window. Same process. And the only difference between this and the texture recognition is we're trying to extract the texture over the whole image. We're not looking at regions of homogeneous texture, as we did in the lectures a couple of weeks ago. So that would be the approach there. So having got the ranking, histogram, and then distance classifier. Or a neural network as well, that's a possibility. IFIER. Right, now we come to the very last approach that was used, and this is retrieval by sketch. And this is where you draw a sketch of the image you're looking for. So here we are. Here is a sketch of somebody I want to find. There's the face, whatever, just caricature. Whoops, don't do that. There it is, a sketch. Another sketch could be, I don't know, a house in the countryside. Smoke coming out, and there's a tree growing there. Using the sketch, and you can use color, you can use texture, you can use the methods we've used above. Now that sounds crazy, and it is difficult to do, but it's needed. And to give you examples where we might want to use searching by sketch. One example I've seen is trademarks. You have a company, you have your design department, design a fantastic logo, which is a trademark, and you want to brand that so that is your property that identifies your product. And what might the trademark look like? I don't know. Something like that. Bit of silly, put a bit of color in there. And if you go to register that trademark, the first question you have to prove is, has anybody else used that trademark? So we've got a database of trademarks. We've got your own design. It has no indexing terms. It's just been designed by you. It has no name, no number, and we can't search on anything but the content. And again, this was a PhD student, PhD project some years ago looking at this. And that is a real problem in the real world. But of course, the bigger problem of searching by sketch, and the more important one, is photo fit. The forensic people want to find somebody. One has a description of somebody who's done something wrong, shoplifting, murder, whatever. Somebody has seen the person, and they can go and they can create an artificial image. An image using all the imaging techniques available to us today to create a picture that looks like the person they're looking for as witnessed by somebody who's seen them. So we end up with an image with no name, no information, just an artist's impression of the person. And we now need to use that image to search a database. The best solution, of course, is to take the witness and expose them to hundreds of thousands of known people in the database and let them make the decision. They are doing searching or recognizing by image content, but it would be nice to automate that and get that into a machine. So again, there's an example of image retrieval, or the need for image retrieval using content. And at that point, I think I want to stop on new material. As I say, next week we will be in seminar mode. Email me with any topics you want me to go over next week, and I will include them in the presentation. If not, when you come online, please give me suggestions and topics for further explanation. As I say, if I hear nothing from you, I will assume that everything is perfect and you know everything, and I'll set the exam accordingly. Just some closing comments. I hope you've found challenges in this AI course. It's been a topic which in the past 5 or 6 years has been very important and received an awful lot of publicity. I would like you to adopt a realistic approach to AI. And although millions of pounds and millions of hours of effort and research have gone into AI in recent times, all we have produced so far is algorithms. And those algorithms seem to work. They seem to work on uncertain data as well as the laws of motion work on deterministic data. The key to AI is consciousness. And I don't mean moral consciousness, I mean just being aware, having meaning for the information. And we still haven't got a clue as to what consciousness is. A car, in an artificial context, a car driving down the motorway, yes, you can have all the equations to avoid collision, all the radar, all the sat navs, all the information possible. But the car does not know what it's doing. It does not know danger. It does not know the limits of its stability. It is just following rules. Humans in that situation bring more understanding, more control, more ability to cope with unseen and unforeseen circumstances. And that really is the key to the future understanding. Whether we get there or not in time, I don't know. All I can say is, back to my original starting point, the brain is an electrical machine. It's possibly the most complicated organ or system in the world. Excuse me. But it is basically a 10 to the 11 electrical processes working together. And the way they work together give us these properties. So we might get algorithms from mathematics, but I think we will get understanding from modeling of the electronics and the electrical processes that go on. So if you follow this as a career, there's a lifetime's work to be done. Good luck. Okay, I'm going to finish now. Any questions from anybody? Sorry, it's been remote teaching this term. I've missed you guys. It's not the same teaching through a whiteboard. It's so much better in the classroom, but there we are. It's the way life has been in the past year. So I hope to see you guys in the flesh next term, or certainly around Brunel at some time in the future. I hope you've got something out of the course. No questions? Okay, guys, good luck, and we'll meet up next week for revision. Bye for now.